Hello again. In this video, we're going to look at a really interesting data set about marathon performances. So just to orient you to what the data is all about, here is the paper that the data comes from. So along with 4 Cornell students, Deb, Jenny, Max, and Angela, we took on the task of studying the impact of a new type of shoes, marathon running shoes, on running performance. So a bit of background, a few years ago, Nike introduced a running shoe called the Vaporfly, and there's actually a few different models of Vaporfly, but we'll call them all Vaporfly for the purpose of this, that have a squishy foam and a carbon fiber plate. And quickly people caught on to the fact that these shoes actually did really help marathon performance. And so mostly the evidence, there was some lab testing and a lot of anecdotal evidence about this. But what we wanted to do was to look at actual marathon performances and look at people not wearing the shoes and people wearing the shoes and figure out what the actual effect is. So what we did in this study is we took a systematic sample of elite athletes taken from performances in 2015 and 2016. And then we kind of followed those athletes over time and looked at their marathon performances and also looked at what shoes they were wearing for the marathon, either non-Vaporfly or Vaporfly shoes, and then did an analysis of the impact of the shoes, controlling for the runner ability and for the difficulty of the specific races that they ran. So the hard part about this study was collecting data on what shoes people were wearing. There's really no data set out there where people say what shoes they're running in every race. There's a little bit of data on some websites, but not really a complete data set. So we combed through photos of marathoners online and tried to identify what shoe they were wearing in each performance. And then we collected this really nice data. And here is the archive webpage where the paper is posted. You can also find it on a website called Researchers One, which is a peer review platform. So there's a peer review of the paper on this website as well. So let's go into R. And so we already have the data set nicely compiled. And let's make sure we're in the right place. Okay. And then the data set is in a directory called datasets, men sampled shoe, and datasets women sampled shoe. So the data are split into men's and women's performances. So let's read those in, and we're going to define a sex variable, and then we'll read in the women and define sex variable for the women. And then we're just going to bind the two data sets together. So before we do anything else, let's just look at the data. So what's in the data set is there's a few name columns. So this is kind of what the raw, from the website we got the performances from, called marathonguide.com. This is what the raw name looks like. And basically what we did is we stripped off the age and capitalized everything. And then we had to do a little bit of manual matching, because sometimes I don't think there's any examples here in the first 6, but sometimes names are spelled a little bit differently, especially if it's a African runner running an American race. They can get the name spelling wrong. So we did our best to match the names, and that's what the match name column is. So this is what we'll be using to identify the runner. And then there's a column for which marathon they ran. So there's these first 6 are from the Boston Marathon, and the year, 2015. And then there's the date of the race, the time. So this is the time that they ran in the race. So this person, Lalisa DeCisa, who's a famous professional marathoner, in 2015 ran the Boston Marathon in 2:09:17. I think he won the race. And if you convert that to minutes, that's 129 minutes, 0.28. And then there's a column for whether or not they wore the Vaporfly. So in 2015, it wasn't widely available, so these are all false. And then there's that sex column. So I'm also going to create another column called MAR year. So it's just pasting the marathon and the year together. That's because when we fit random effects models, we're going to have a different effect for each marathon year combination. And then I'm going to make sure the date is coded as a date. So before we get into the analysis, we're just going to do a little bit of exploratory analysis and plotting. So here what I'm doing is I'm using the table function to count up the number of performances at each marathon year combination and separate it out by sex. So let's see. So here, what this means is Boston Marathon 2015, in our data set, we have 24 females and 31 males. Let's see, the big ones in this data set are Boston, Keller International, which is in Sacramento, Chicago's a huge marathon, and then we also have some smaller marathons as well, Columbus, Eugene, Grandma's is a pretty big one, Houston, Indianapolis, LA, New York, Philadelphia's pretty big. And there's we have a marathon, the Women's Olympic Trials in 2016. That was in February 2016. And we have the Men's Olympic Trials somewhere. So here, of course, they're all men. And here, of course, they're all women. So we're interested in the impact of the shoes and additionally whether there's a different impact for men versus women. So we can use the tapply function just to do a really simple analysis to apply the mean function to every combination of the sex and Vaporfly variable to the variable time minutes. So if we run that, what we find is, so what this means is on average in our data set, females who did not wear the Vaporfly ran 160.6 minutes. So that's about 2 hours and 40 minutes. With the Vaporflies, they were a little bit faster, about 2.7 minutes faster. And for the men, the average non-Vaporfly time was 139 minutes, so that's 2 hours, 19 minutes. And with the Vaporfly, it was 136 minutes, so that's 2 hours, 16 minutes. So, of course, this is not quite the right analysis because, so for example, what could be happening is that we have a bunch of men in the data set, and it could be that the faster men are adopting the Vaporfly shoes, and the faster women are adopting Vaporfly shoes. And that's why the times tend to be faster in the Vaporfly group than the non-Vaporfly group. So there's alternative explanations to this that don't involve the shoes having any benefit or not. So what we really need to do in our analysis is control for the strength of the runner who's wearing the shoes. And also, maybe less likely is that maybe people are wearing the Vaporfly shoes in marathons that are faster. So, for example, the Boston Marathon tends to be a pretty slow marathon because it has a lot of hills. And the Chicago Marathon tends to be pretty fast because Chicago's very flat. So if it were the case that people were wearing Vaporflies at the Chicago Marathon and wearing non-Vaporflies at the Boston Marathon, that could produce these results as well. So we'll want to control for the difficulty of the marathon as well. Now let's look at some plots of the data. So what I'm going to do is I just want to make a kind of a time series plot where on the horizontal axis we have the date and the vertical axis we have the time. But I want to separate things out by male and female performances. So I'm going to use color for that, blue for male, magenta for female. And then I want to use a different plotting symbol for vaporflies versus non-vaporflies. So for non-vaporflies, we're going to use plotting symbol 1. And for vaporflies, we're going to use plotting symbol 3, which is a plus. I'm also going to just slightly offset the female times from the males because at a big marathon like Toronto Marathon, you're going to have everybody competing on the same day. So it can help visually if we just offset them a little bit. All right, so that's that plot. What we can see is that women tend to run slower than men. Okay, that's known. What we also see is that, so the pluses are the vaporflies. What we also see is that there are very few pluses in 2015, 2016, and even into the first half of 2017. There are a handful of pluses, like this one, for example. So this is, this is the Olympic trials in 2016. And what's going on here is that there were a few professional Nike athletes who did have access to the Vaporfly shoes before they became widely available. So that's what these pluses are. But it wasn't until basically the second half of 2017 when they become publicly available and people started wearing them. So you start to see a lot more pluses, especially the very last race, which I believe is California International Marathon 2019. A whole lot of the field is wearing the Vaporfly shoes. So people, the idea here is you can see that people are catching on to them and they're gaining widespread adoption as time goes on. Okay. So this is, maybe you could argue this is a little bit cluttered. So the next plot, it just separates things out by year. And so maybe this is a little bit easier to digest. So here's 2015, 2016, 17, 18, and 19. So I'll just leave that up for a second so we can stare at it. Another thing that's a little bit clearer from this plot is that there's really there's a marathon season where the top runners run at marathons. So this is probably Houston Marathon in January. But aside from Houston, there's a spring season starting in mid-March. And then there aren't many major marathons in the middle of the summer when it's really hot. And then there's a lot of fall marathons like Chicago and New York. All happen in the fall. All right, so the point of this is we want to fit some models and we want to control for the difficulty of the race and the ability of each runner. And we're going to use LME4 to fit our random effects model. So what the first model does is it takes the time in minutes as the response, and then there's going to be a fixed effect for Vaporfly, and then we're going to control for marathon year and the match name, which is just a variable indicating which runner is running. We're going to use DAT, and we're going to fit separate models for male and female just to start with. Okay, so here's the result. What do we find? So this is the variance of the runner effect. So I think this makes a lot of sense that the ability of the runner makes more of a difference than the difficulty of the course. So if Lalisa DeCisa runs Boston Marathon, which is a slow course, and I run Chicago Marathon, which is a fast course, Lalisa DeCisa is still going to beat me by a long shot. So there's more variation in the ability of the runners in our data set than the difficulty of the races. But then there's still a lot of variation left over at the end. So the residual variance is about 16.9, which is about 4 minutes on standard deviation scale. So there's still a lot that can impact the race, even if you control for what shoes they're wearing, who's running, and which particular race they're running. Okay, and here you can see the Vaporfly effect, which is the effect of interest in this analysis, and it's minus 3.12 minutes for a marathon. So just to give some context for that number, these top elite marathoners are running the marathon in 5 to 5.5 minutes per mile. Some of them even faster than 5 minutes a mile. So 3 minutes is well over half a mile. So what this is saying is that if you wear the Vaporfly and your equally strong competitor is not wearing the Vaporfly, you can expect to beat them by 3 minutes, which is half a mile up the road at least. So this is actually a pretty big effect and is significant. So the t-statistic here is minus 5. Okay, let's do the same thing for the women. So that's the same exact model, but we're subsetting sex equals female. And we get similar effects here. One thing is that there seems to be a bigger spread of abilities of women than men. The year seems to have the marathon year seems to have a bigger effect. And there also seems to be a larger residual variance, about 5 minutes instead of 4 minutes. The Vaporfly effect is smaller, but it's still negative, and it's still significant with a t-statistic of minus 2.8. So here for the women, it's about 2.3 minutes. Okay, so another thing we might consider is, so in these models, what we're saying is that the Vaporfly has an additive effect. If you wear it, you get better by 3 minutes. But it may be more appropriate to say, for a mediocre runner who runs a marathon a mediocre elite runner, I guess I should say, who runs a marathon in 2 hours and 20 minutes will have a bigger effect than an elite runner who runs it in 2 hours and 5 minutes. And so maybe the effect is multiplicative instead of additive. So the way you fit a multiplicative model is one way of doing it is you can take the log of the response instead of the raw response. So that's what M3 does for the males. And here's the summary. So how do we interpret this? So these are standard deviations on the log scale. These are multiplicative effects. And so the way we interpret this number, well, let's start with this one. There's 4.93. So what this says is if we do e to the 4.936261, so we get about 139 minutes. So the expected time, e to the expected log time is about 2 hours and 19 minutes, which is pretty close to what we got with this model. So that checks out. And what this says is the effect of the Vaporfly is you take that expected time and you multiply it by e to the minus 0.02. So let's look at what that is. So this is e to the minus 0.022. It's about 97.8. So the Vaporfly time should be 0.978 times the non-Vaporfly time. In other words, it's about 2.2% lower or faster. Okay, so that means that the Vaporfly has a impact of 2.2%, and what's constant is the multiplicative effect of the impact in this model, whereas in the other model, the impact was additive. We could do the same thing for women. We get a similar effect here. It's about 1.44%. And so another thing, a nice feature of the multiplicative model is now the impacts for the random effects for women and for men are more similar. So for example, for the women, the residual variance is now 0.0299 and the men is 0.028, which is much closer than 4 versus 5. So that makes the models more similar. This is important because what we're going to do next is we're going to put the women and men in the same model. And because the log models between women and men are more similar than the additive models between women and men, we feel more comfortable putting the women and men together on the log scale. Okay, so let's do that, and that's the last model that we're fit. So if we run that model, so the way we do this is we do log on the interaction between Vaporfly and sex. We want to know what's the impact of Vaporfly for each sex. And then we have the same random effects. And here's the output. So again, we get about 0.029 for the residual effect. And for the Vaporfly effect for women, it's about minus 0.017. And then the Vaporfly for men is slightly higher. It's minus 0.023 or 4 roughly. And the women's Vaporfly effect is statistically different from 0. We have a large t statistic. But the t statistic for the interaction is only minus 1.17. So even though we estimate the effect of Vaporfly to be larger for men than for women, we don't have enough evidence to say, to conclude with any confidence that they are actually different. So we know that by looking at the t statistic for the interaction. So we can say that we have pretty strong evidence that there is an effect. But the results are inconclusive about whether the effect differs for men and for women. If we had to guess, it's better for men, but we don't have strong evidence for that. All right, so we have our main conclusion that there is a significant Vaporfly effect. It's both statistically and practically significant. But we don't have evidence that the effect differs for men than for women. So just for fun, since we fit this random effects model, I want to look at our estimates of the effects for the different runners and for the different race. So, and we're going to use this M5, this log model that combines men and women. And there's a function called ranf that allows you to extract random effects. So if we do ranf M5, these are all the random effects. These are the runners, and these are the races down here. And so I'm going to pull out the runner effects by looking at the match name. Let's see. And I'm going to look at the race effects by pulling out the Mar year random effect. And I'm going to order them by who has the most negative effect, and then print out a data frame of all the effects. So it didn't print all of them out, but we can look at who the top runners are. So this says that the best runner in our data set is Mary Keitany, which is not surprising. Mary Keitany is a very famous female marathoner from Kenya. And second best is Desiree Linden. So Desiree Linden is an American marathoner. She won the Boston Marathon in 2018. And then we have Florence Kiplagat, another famous person. Kellen Taylor is a top American runner. Edna Kiplagat, very famous. Kara Goucher. All the top ones are women. This could be due to the fact that there was more variation in the women's abilities than the men's. Let's see. Top man. Albert Corrier is not super famous. But then we have Lalisa DeCisa, Jeffrey Camerwar, Shadrach B. Watt, he's American. Galen Rupp, is one of the top American, probably the top American runner. All right, so this kind of makes sense. Oh, another one is Jared Ward. Jared Ward is an American runner who is also a statistics instructor at BYU. Okay, so those are the top runners. If we look at the races are kind of interesting as well. So we'll start down here. The slowest race in the data set is Boston Marathon 2018. So the slowest race, according to our model in this data set, is Boston Marathon 2018. This makes a lot of sense if you follow running at all. Boston Marathon 2018 was a particular bad weather year for the Boston Marathon. There was a headwind and rain, and it was very cold. So this is by far the slowest race in the data set, which makes a lot of sense. So this is some evidence that the model is doing something reasonable. And you can also see that Boston Marathon has a bunch of the slowest times. So Boston Marathon 2018 is the slowest, but 2016 was slow. 2019 was slow. Did I skip any? There may be others as well. And then looking at the list, the fastest ones are Ottawa Marathon. I don't know much about the Ottawa Marathon, but Houston Marathon is a very fast course. Toronto is a pretty fast course. Chicago, I already mentioned, is a very fast course. Indianapolis, very flat as well. Cal International is a very fast course. So it's giving us things that make a lot of sense. So these are all fast courses. Let's see. Grandma's in Duluth, Minnesota, very fast course as well. Okay, so this gives us some confidence that the model is doing something reasonable. All right, the last thing to look at is I want to see if we can recover the fixed effects estimates using our model estimates. So the first thing I'm going to do is I'm going to take the data and remove the missing value. So this is the data we're going to use. And to create the covariance matrix, we're going to look at we're going to add the runner effects to the race effects. And the way we're going to create these matrices is I'm going to create a kind of a design matrix for the runners and the design matrix for the races. And I'm going to do the outer product in order to create those matrices. So the design matrices I'm calling Z. So this is the runner design matrix. This is the race design matrix. And then I take the outer product to get a block diagonal matrix. And then I also have the variance of the residual. And this is how I extract the covariance parameters. So this may look a little bit weird. I had to look this up to figure out how to extract the covariance parameters correctly. But these are the parameters. Let me convince you of that. Covparms. So 0.0012, 0.00034, 0.0008. Those are these numbers here. And then to create the covariance matrix is just the runner covariance parameter multiplied by the runner matrix, the race covariance parameter multiplied by the race matrix, and then the residual. Create the design matrix with model.matrix. This has the Vaporfly sex interaction. my response is the log of the time in minutes. And then beta hat is just X transpose sigma inverse X inverse times X transpose sigma inverse Y. And there's beta hat. So this column should match this one up to rounding differences. Okay, so that is the Vaporfly analysis. We found that there was an effect, and then we looked a little bit in further detail at the actual random effects and saw that those kind of made a lot of sense. And then we were able to reproduce the estimates by hand.